Good morning, my name is Luca Visinelli. I'm a tenure-track associate professor at Shanghai Jiaotong University, and I'm also affiliated with the Tsung-Dao Lee Institute in Shanghai. I graduated in December 2011 from the University of Utah in Salt Lake City with a thesis on the role of light bosons in cosmology and astrophysics. This is the line of search I kept pursuing over the following years. Since then, I have been hired by two of the most important institutions in Europe, namely Nordita in Stockholm, Sweden, during 2016-2019, and Grappa Amsterdam during 2019-2020. In 2020, I have won a Marie Curie Fellowship under the Fellini program issued by the Italian National Institute of Nuclear Physics, prior joining my current affiliation at Shanghai Jiaotong University. These positions have established me as a mature researcher and allow me to create a strong international network. In my work, I explore the nature of dark matter and dark energy, which are two distinct manifestations of new physics not contemplated by the Standard Model, for which we have no other clue besides their gravitational interaction. Understanding the nature of dark matter and dark energy is crucial to advance our knowledge of the physics beyond the Standard Model of particles. This is the main activity at Shanghai Jiaotong University. I focus on the interpretation of combined observations from cosmology, astrophysics, and from laboratory searches in terms of new light boson fields, which are a common prediction of string theory compactifications. I first discuss some of my contributions regarding the theory of dark energy. Using data from the cosmic microwave background, I have constrained the properties of light bosons as dark energy. In the same work, I have also shown how string theory can be tested through the cosmology of the light bosons. Recently, with colleagues in Shanghai, we showed that the birefringence detected by CMB data can be explained if the dark energy is modeled as a light pseudoscalar field. I have recently considered models of light bosons produced in the Sun and detected at Earth in the laboratories otherwise designed for the detection of heavier dark matter candidates. Thanks to this advancement, I have been awarded the 2021 Buchalter Cosmology Prize, issued by the American Astronomy Society. My second biggest contribution to the field is my activity in understanding the physics of the axion. The axion is a pseudoscalar particle that couples to gauge bosons and which can solve the strong CP problem of the QCD sector. It has been introduced by Professor Frank Wilczek, the founding director of the Tsung-Dao Lee Institute in Shanghai. In my graduate work and in many other papers afterwards, I have shown that the mass of the axion dark matter particle can greatly vary from what had been usually believed because of the uncertainties in the cosmological history. My work has motivated the search for this particle even in ranges of mass that were not considered before, and it is now a standard practice to consider an enlarged axion mass phase thanks to my pioneering work. Another prolific line of search is the assessment of dark matter substructures in the galaxy. I am working on axion substructures in the Milky Way by assessing their abundance from Monte Carlo simulations applied to the state-of-the-art modeling. I show that axion substructures could lead to transient radio signatures that are potentially detectable with radio telescopes. With my colleagues, I am testing the model against data that have been collected from radio observation in the Andromeda galaxy. My review papers, one for the axion, one for dark energy models, have been extremely precious for the community and have established me as an expert in the fields. The comprehensive review from 2020 on the axion has been cited more than 450 times. The review on the cosmology of the Hubble tension has been cited more than 850 times and has helped collecting the scattered literature on the subject. To sum up, I work in particle astrophysics and cosmology, testing theory of new physics against data. I am particularly active in the field of light bosons. I have published 60 papers in the topics gathering more than 5,500 citations, with an H index of 39. I have 2 PRLs, 9 single-author papers, and 18 first-author papers. During my activity, I am extending the progresses of my graduate work. incorporating new theories and experimental activities. I am actively training new master and PhD students. I will discuss one of the projects outlined in the grant proposal. I propose to test the theory of the axion using gravitational wave detectors. The interplay of light bosons and gravity has been explored in the past. However, I plan to link my research to the model of the QCD axion, which is well motivated as the solution of the strong CP problem, and I plan to link the work to the exploration of the cosmological history of the universe. The axion field originates from a phase transition in the early universe. A primordial phase transition would lead to distinctive signatures. First of all, primordial gravitational waves. Second of all, the production of topological defects such as cosmic strings. Since we do not observe strings today, cosmic strings must have dissipated by radiating a mixture of hot and cold axions. The very recent discovery in June 2023 of the gravitational wave background by many collaborations, including Nanograv and the FAST radio telescope in China, show a concrete pathway to explore the nature of the dark sector through these methods. I am interested in assessing the gravitational wave abundance in cosmological model of axions to have a joint prediction that can be tested both from gravitational wave detectors and in the laboratory. Joint signals are beneficial since they increase the confidence in the cosmological model and in the nature of the dark matter particle. I have shown that the evolution of the axion field in the early universe leads to an imprint of gravitational waves and other signatures that can be detected with these new techniques and with future gravitational wave experiments. This is the figure to the left. Detecting this imprint would shed light on the cosmological history of the universe. I want to refine the analysis both with improved methods and with data analysis. One of my students in Shanghai will refine the computation with a numerical simulation of the string network. Ideally, we should be able to assess the gravitational waves and isocurvature modes produced in this model against data from CMB and from gravitational wave detector reaches. Since we now possess both datasets, simulations of this type are rather expensive computationally. However, the Jiao Tong University possesses a cluster consisting of around 60,000 nodes available and would allow us to provide the first and most updated simulation in the field. My proposal goes in the same direction as my previous research career and aims at exploring the existence of the axion using astrophysics and cosmology. My emphasis is on the theoretical aspects of the axion, although I am in close contact with experimental efforts. So far, I had one postdoc, Michael Zanteteschi, who got his PhD from Munich and joined in November 2022. I am training the three students, Hanyu Cheng and Ziwen Jing, who are PhD candidates at Shanghai Jiao Tong University, and Kixuang Su, who's a master student from the UK, who's planning to visit SJTU for a year starting October. The grant will allow me to hire one additional postdoc and up to 3 graduate students, which will split forces among the different projects. All results will be presented in dedicated conferences at the international level during the summer periods. Training the next generation of researchers will strengthen the position of China in the field of precision particle astrophysics, which is a mature subject that is gathering important achievements worldwide, with more Nobel Prizes to be shared once the nature of the dark sector will be unveiled. The dark sector will be explored through a joint analysis of gravitational waves and cosmological datasets. I am among the pioneers and forefront persons for this. The potential rewards of this project are: first, if the axion is discovered, its key features would shed light on the details of the new physics beyond the standard model and pave the way to future progresses in both cosmology and fundamental physics. Second, a cosmic background of axions could account for the dark matter observed. Third, if the axion is discovered, it would solve a major problem in fundamental physics. Thank you for the attention.